Good morning, friends. Welcome back to your favorite class on composite materials in our quarantine life. Awesome. Kind of rainy and gloomy out there in Milwaukee right now. Just got my dog all at Twitter, but he'll survive. Okay. Right. Announcements. Hopefully you got your homework in. If not, what are you doing? Get it in. I posted a new homework on fracture mechanics. I finished it up yesterday. That is posted. 3 problems. You should be able to tackle them probably not after today's lecture, but after Monday's lecture. It's going to be due next Friday. All right. So I'm anticipating the discussion of fracture mechanics probably through next week, Friday. But the homework problems you should be able to do probably after Monday or Wednesday's lecture. All right. So that's announcements for the class. All right. Without further ado, let us continue our discussion on the awesome world of composite fracture mechanics. The boring world of Niels Bohr. All right. So recall we're talking about fracture mechanics. And yesterday I talked about the main metric that we use to evaluate fracture in composites is the critical strain energy release rate. Right. Usually that's given with the variable capital G and sub C, critical strain energy release rate, G sub C. This is measured in joules per meter squared, or the equivalent English value, which is like BTUs per inch squared. Yeah, right, exactly. Okay, joules per meter squared, much more appropriate values here. And what this is like an energy per crack opening area. So here, this is like an energy value. So how much energy, in terms of like if I'm loading up a piece, we can determine how much energy is associated with that. It's like the integral under the curve. The energy required to open a crack a certain amount. All right, pretty straightforward. We looked at the different modes of fracture. So I kind of drew for you those modes of fracture. We talked about those. And I'll just bring this picture in again just to reinforce that, is that you have these 3 different types of fracture. That is mode 1, this Pac-Man mode. Rawr, Pac-Man. All right, mode 2 is in-plane shear. So that's like your deck of cards example. I wanted to bring a deck of cards in, but I forgot. So you have these layers, and when you put some load on them, they kind of slide against each other. All right, so that's this in-plane shear. The loads are in the same direction as the crack propagation. And then mode number 3 is the trouser tear. Okay, so it's like ripping a piece of paper. It's the out of plane shear. The loads are not in the same direction as crack propagation. All right, so those are the 3 kind of modes. And we said that each one of these has a different critical strain energy release rate. Okay, and we label that with like a subscript, Roman numeral 1, 2, or 3. So this is like, you would write G1C, here this is G2C, and you guessed it, G3C. All right. Not to be confused with 3G, which is what your phone uses, or G4C, 4G. I don't know. All right, so those are your modes of crack opening. And like I said, the metric that is going to be useful for us is energy per crack opening area. So something like joules per meter squared, right, is the unit, and that's for all of these different types. All right. So with this, we need to have a discussion about energy because this is an energy-based method, right? So it's an energy-based theory. We need to have a discussion about energy. All right, so let's take a walk down memory lane back into your like 3005, 2004 classes, mechanics and materials, talking about work and energy from external forces that are done on a piece. All right, so when we load up some solid, all right, let's make our famous, world famous mechanics potato. All right, so solid body. All right, let's put some coordinate system on here. I don't know. Random in space. Here's X, Y, Z, random in space. And I'm going to put some force and some moment on this. All right, so here is some external force, F with a dash over it because I'm drawing a vector here. And maybe there's some moment that acts on this guy. Double arrow for moments here. All right, so this is loading up some solid, however we do that, with forces, with moments, with torques, whatever. All right, then the energy associated with that, we typically write as U1 to 2. The work put on the object as it's moving from location 1 to location 2. Think back to your ME2003 class, you should have had this definition. This is something like the integral of the force dotted with path plus the integral of the moment dotted with the angular path. All right. More comfortable people might see this as like from location x1 to x2 of fx dx, and so on and so forth for the y direction and the z direction. And then this guy expands out to similar idea, mx d theta x from theta x1 to theta x2 plus dot 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 dot. Okay, so the idea here is that the work that is done is the force integrated over the path. All right, so hopefully this is something that you've seen before and should be pretty well understood at this point. All right, so this is work that we apply to a piece, right? That's our definition for what the work is done that's applied. Now, that work goes somewhere, all right? That energy that we put into the sample goes somewhere. When we're loading up a solid material, it can go to elasticity, right? Deforming the material. It can go to plasticity, which is kind of slipping planes across each other if you're talking about metals, or crazing in plastics, or some of the other metrics associated with plasticity. It can go towards kinetic energy. So if I load something up and it's not static, it can move. All right, so that's another place where it can go. It can go towards heat. It can go towards sound, right? So if I load something quickly, maybe there's sound associated with that, and that's energy that's being released. There's all these sorts of things that can, release energy, or where the energy is stored inside of the piece. One thing that can also be done with that energy is to create free surfaces, which is fracture. All right. So let's expand on that. Energy from the loading can go to many places. All right. So the ones that we'll talk about, and the important ones for us, are elastic strain energy, usually we'll denote this with the variable U sub E. This is energy of elasticity. And here, this is energy which is recovered after loading. So think about like a rubber band. You pull on a rubber band, you've externally loaded it. Once you release that load, it responds. All right. So this is recovered energy of deformation. I don't want to say recovered, recoverable. All right. Recoverable energy from the deformation of the body. There's also plastic strain energy. Given by the variable U sub P. And this is unrecoverable deformation. So hopefully you saw plasticity in your material science class. You like loaded up some steel member or some aluminum member until it started necking. And then when you release the load, there's that permanent deformation that exists there. That's the deformation or the energy associated with permanently deforming the body from plasticity. When you load something up and it's not static, it can move. So it could go to kinetic energy. Given by the variable, usually capital T. This is the energy of motion. Right? If I load something up and there's nothing to resist that object, then it's going to move. Right? Finally, the one that's important to us is the energy that could go to, it's known as dissipative fracture energy. Given by the variable capital D. All right, this is the energy associated with creating a free surface or fracture. And this is where we're going to kind of focus our energy. All right. So we can write this mathematically. I'll make one more note, is that there are other sources that are negligible. So things like heat. I'll write heat with kind of a caveat here, in that sometimes the energy of heat is not negligible, but for what we're talking about in this class, negligible. Heat, sound, others, blah, blah, blah. Sometimes light is created. Look up triboluminescent materials. That'll blow your mind. All right. So other negligible sources, heat, sound, so on and so forth. All right. So mathematically, we have this like energy balance because, energy is conserved. And we have something like the total work that we put in from external forces that we apply, these forces, these moments, etc., is a combination of the elastic energy and the plastic energy and the kinetic energy and the dissipative energy from fracture. This was kind of like our baseline, very simplistic elementary 101 energy conservation equation. COVID. All right. So mathematically, energy is conserved. Energy of elasticity, of plasticity, kinetic energy, fracture energy, all has to be balanced out by whatever work that we put onto the system in the first place. All right, that's kind of the idea here. So when we're working with composite materials, we're going to kind of assume that there's no motion. So let's get rid of that guy straight away with our analysis. Assume no motion, such that t is equal to 0. All right, so that's, I just want to write it in the most general form here so that you understand that, yes, it could move if we're not considering that. But let's say that we don't have that general motion consideration. All right, so this is kind of where we're going to start with our analysis. This idea of whatever work we provide has to be balanced by the elastic energy that we provide, the plastic energy that's inside the sample, and the energy from fracture that we create. All right, so that's the general basic idea. Now let's look at what happens when there is no fracture, just to make sure that we're on the same page. All right. So review, no fracture. So here, this is when D is equal to 0. All right, so we're not creating any free surfaces. We're just having this balance between elastic and plastic strain energy. All right, so let's consider aluminum bar in tension. All right, so that might be this guy here, and we're loading this guy in pure tension as such. All right, so here we have like load that's generated equal in both directions, and let's track how the load displacement of this might look over time. Right. So if we load this up, we're going to have displacement on the x-axis here, and we'll have load on the y-axis, obviously. When we load this up with like your standard uniaxial tension test, what's going to happen for this aluminum member is obviously it's going to have some linear response, right? So we know that it's this linear elastic material, loading, loading, loading. And then at some point it's going to reach its yield stress, so it'll sort of curve over like this. And then if we were to unload it, it would unload with the same modulus as this guy here. Okay, so I'll try to draw that as best I can. All right, so here's your elastic modulus E, and we're also unloading with that same elastic character E, and we're loading up here. Here's our yield point, and this is generally how the material will behave. It reaches some maximum value of load and displacement. Let's say that this is point A, and it's got maximum displacement here, delta final, and it's got maximum load here, P final. All right, so these are like your XY coordinates of this particular point, right? Well, if we look at our energy balance, we'll say that the total work is equal to the energy of elasticity plus the energy of plasticity. Remember, we don't have any dissipative fracture energy in this particular situation. Well, the elastic energy is the recovered energy. All right, so remember that our total work is equal to the integral from 0 to delta final of the load that we apply. So here this is like P as a function of delta, d delta. So the total energy that's done up to delta F, which is here, is the integral under this curve. So the total energy is here. All right, forgive my terrible sightings there, but here this is the total work. All right, so the total work that we put into the sample when we're at its sort of like maximum displacement. All right, so this would be the integral under the curve. All right. So that's the general equation for the total work that is done. You need to know what that total work is to balance it out appropriately. All right. Back to this figure. I want to have to draw it again. So there's your total work, and that's balanced by the energy of elasticity and the energy of plasticity. All right, so the energy of elasticity is the energy that is recovered. So this is the energy that was recovered. And that is UE. And the energy that was not recovered is here. And that is the plastic strain energy, UP. Okay, so when I say that the total energy has to balance both the elastic and the plastic strain energy, well, the amount that we recovered there in blue plus the unrecovered plastic strain energy there you see for UP is going to be equal to the total work. All right, it's kind of pretty straightforward. All right. So it's not exactly accurate to say that this is the modulus, but I wanted you to think about that when I originally drew this. this isn't actually the modulus. This is something known as the compliance. So it's related to the modulus, and this will be important for our calculations in just a second. So here, the recovered energy is something that we can sort of talk about quickly and come up with like a mathematical expression for what that is. All right. So the elastic energy under curve is a triangle, right? So approximated with the elastic energy here, area of a triangle, 1/2 base times height. So here, this is 1/2 my base. Here I have the final displacement of my total loading. And let's say that it unloads and has a residual displacement down here, which I call delta P. This is known as the plastic displacement. Right? Plastic displacement is the displacement that the piece has after it's been unloaded because of plasticity. Sort of makes sense, right? So if I pull out this aluminum bar and then I unload it, it's going to unload and shrink back down, but it's going to have deformation beyond what it originally had. That's called the plastic displacement. So here we can approximate the elastic energy that was inside of the sample as 1/2 the base, which is delta final minus delta plastic, times the height, which was the maximum load that we had on this piece, which is PF. So this will be an important finding for us here. So this is an estimate for the elastic energy. Right. So if we do some experiment, we load some bar up, it goes plastic, then we unload it. If we know the maximum load, if we know the maximum displacement, and we know the plastic displacement, we can figure out what the elastic energy was inside of that sample. Right? You just kind of like look at this load displacement curve and sort of figure it out. Right? So that means that the plastic energy is whatever work we put into that minus the elastic energy. Right? We would say that the plastic energy is the total work minus the elastic portion, or we know the total work to be the integral under the curve of this load displacement. So this is the integral from 0 to delta final of this load as a function of displacement integrated over the displacement minus the energy associated with elasticity, or the recovered energy, which here is 1/2 our base, which is delta final, minus delta plastic times the final load. All right, so here is your plastic energy inside of the sample. Okay. So reminder that here in red is like your plastic energy. Right? This is the unrecovered energy. So hopefully we're starting to sort of understand a flavor here of like where the energy is going, how we can maybe use load displacement curves to calculate what the energy is associated with elasticity, with plasticity, so on and so forth. Okay. And that's generally like for a metal. All right. But we haven't talked at all about fracture. And we know with composites, we're generally brittle. So we're not going to have a lot of plastic energy. Okay. I just wanted to kind of like go through a quick review on elasticity and plasticity, load displacement, what it looks like, how we can pluck those off as a sort of preparation for what we're going to talk about next. And so let's go back to the general balance. And here we're neglecting kinetic energy again. So here we have the total work that you put into the sample is the elastic energy plus the plastic energy plus the dissipative work of fracture. Right? And I'll say here that because we're dealing with composites, and we will make the assumption in this class that all of the matrices and all of the materials in our composites are going to be brittle, that we will have no plasticity. I will say, in reality, that is not the case. I know this firsthand, that most composites actually show a very small amount of plasticity regardless of the matrix material that you select. And so doing this analysis as we go forward makes the assumption that everything inside of it is brittle, which isn't always the case, especially if you have things like a thermoplastic matrix. That definitely ain't brittle. All right. If you have rubber toughened matrices, not brittle. All right. So you have to be aware that if you're going to do this analysis that I'm going to kind of prescribe over the next couple of slides, the matrix materials must be brittle. All right. So here, let's assume brittle matrix phase such that the plasticity is equal to 0. All right. So there would be no turnover in the load displacement curve. All right. This is a good assumption for most pure resins. Like epoxy and some vinyl esters and other brittle matrix phases. Not good. For thermoplastics. So that would be like polypropylene, polyethylene, PEEK, so on and so forth. Or rubber toughened matrices. We'll talk about those in just a second, probably on Wednesday of next week. So it's not good for thermoplastic or rubber toughened matrices. And that's because you can't neglect plasticity in those particular cases. But let's say that we can neglect this plasticity. All right, well, now it's time to talk about the work associated with fracture. We have this simple energy balance, that the total work is equal to the elastic energy that you put into the sample plus the dissipative energy of fracture. This is our general baseline equation now that we're going to sort of balance out and look at over the next couple of slides. All right. Before we get into composites, let's just consider the brittle matrix phase itself. And let's assume that we have a block of matrix material that has a small crack in it. Okay, so let's set that situation up. All right. So here's our matrix material. We've got some crack in it here on the side. All right, I'm kind of exaggerating this guy. So let's label this. I'll call this A0. This is the initial crack length that we have to work with. All right, it's A0. All right. Let's say then that we're going to load this guy up with some particular load. All right. So I'm going to load this guy up in this general direction. So this is a mode 1 type loading. It's like the Pac-Man, right? Pac-Man, mode 1. Rawr! Right? Let's say that I'm loading this up with some value of loading P1. All right. Let's just call it P for now. So let's look at the load displacement and what might happen with the load displacement as this thing is being loaded. All right, so here's the displacement. Here's the load. What's going to happen to this guy? All right, well, I'm going to pull it. I'm going to pull. There's not going to be any plastic deformation. It's all going to be elastic. It's all going to be recoverable energy. But at some point, I'm going to pull, and that crack is going to shoot across and grow some length. All right, so the way that we'll represent this is we're going to load this guy up, load. And at some point, we're going to have enough load on there so that the crack can't stand it. It's Popeye. It can't stands no more. All right. It shoots right through the piece. So what happens here is that we've reached some maximum value. Let's call this point A. That has some final displacement and some load. Let's call it P1. Right. And what happens is load. We'll assume we're in displacement control, so the displacement stays the same, and a crack is formed, and a lot of the load that's on the piece is relieved, okay? So what happens is we have this massive reduction in the load as the crack propagation occurs. That's crack prop, and that's what's happening when we're going from that current value to, if we're in displacement control, this other value down here, which would be point B, that has the same displacement, delta F, and now a different load here, which is P2. Right? So that's what's going to happen if we load. There's going to be a crack that's generated that relieves the force that's on the piece. All right? So we've got this now large crack. So we load, and we get to the value of P1. So this figure here is right before failure. The crack has not yet propagated. It's still at whatever original length it had, A0. And right after failure, we'll have the same displacement. So it'll look pretty much exactly the same, except here we'll have an additional amount of crack that has grown. So if this was our original crack length, here's A0. Now this will have grown by some additional amount. Let's kind of highlight this in red, and I'm going to really exaggerate this. And this has grown by an amount which we call delta A. All right. So the crack has gone from the original amount, A0, to a new length, which is A0 plus delta A. And that occurs, you jump to this new load, which is P2, where P2 is less than P1. Because we're relieving the load that's on the piece by creating this new fracture surface. All right, I say right before failure, but better to say right before fracture. All right, so that's what we're trying to depict here. We load up. Can't stand it anymore. Crack happens, bang. All right, we have to relieve the load so that we're not so stressed out. All right, sounds like me in quarantine, right? After that crack has occurred, let's say that we're like, oh crap, we just made a crack in our piece, let's unload. We're still going to unload in a purely elastic fashion, meaning that the energy that's inside of the sample now is still only elastic. All right, we still haven't included any plasticity in this particular piece. So when we unload this piece, it's going to return to its original character. All right, it's going to return back to its original length. And so what happens is when you unload, it returns back to its original position. So even though it's got this massive crack that's formed, there is no energy associated with plasticity that we put inside of the sample. So you load this, a crack happens, then you unload, it will still go back to its original position, but you have this massive new crack inside of it that has formed, right? So this is the general schematic that you should have in your head of like what happens with a single fracture event. All right. So let's look at what the energy is associated with this particular happening, right? So we know that the total energy this WTO, is the integral from 0 to delta final of the load as a function of the displacement integrated over the displacement. So the total work that is done is the integral over the entire thing here. That is the total work that's inside of the piece. All right, so that's the integral of this loading curve up to the maximum load and displacement. That's your total work. All right, that is this portion of the equation. All right. The elastic energy, this is the energy that was recovered, is going to be given by this here. This is your elastic energy. All right. So this is the amount that was recovered after we had our fracture event and unloaded our piece. That's the amount of elastic energy that we recovered. You can come up with a mathematical expression for this because it's a triangle. All right. So it's pretty obvious to see that the triangle has coordinates 0, 0. This point here, remember, is delta F. All right. And then the height there is P2. So this is just the triangular area, which is 1/2 times P2 times delta F. All right. This is your elastic energy from this particular fracture event. All right. The total work that we put in can also be defined mathematically in a similar way. All right. This is going to be 1/2. Okay. So again, we have like a triangle. And this triangle is made up of 1/2 times now P1 instead of P2 times delta F. All right. So that is, this big triangle here, this guy. All right. Remember our general equation. Here, we can rearrange this and say that the dissipative energy from fracture is equal to the total work minus the elastic contribution. So what this is graphically is the dissipative energy from fracture is this amount of energy here inside of this load displacement curve. That is here. Okay, here is your dissipative energy from fracture, capital D. Okay. This is the energy required to open the crack a certain amount. So it is this total work term, which is 1/2 P1 delta F minus the elastic recovered energy, which is 1/2 P2 delta F. Or if you want to write this by combining terms, you can say that the dissipative energy from fracture in this situation is 1/2 delta F times, did I get this backwards? Yeah, I think it's backwards on the P1 minus P2. It's backwards in the notes. Apologies for that. I'll have to update that. Page 9 of the notes, is incorrect. This is the correct formula. All right. So this is the energy required to propagate the crack in length, spelling is hard, of delta A. All right. So we loaded this guy up, loaded him up. He failed. The crack propagated this distance delta A. And we determined that the energy associated with that particular fracture, because of the only place where our work can go is either elasticity or fracture. We figured out what the elastic recovered energy is here. Then the remaining energy which exists, which is this triangle here, is the energy associated with the fracture. And we can kind of understand that mathematically as this particular expression. All right, so that's the energy associated with fracture. The units on this are like joules. All right, so we're not quite done yet with getting to our critical strain energy release rate, because we know that that's in joules per meter squared. All right. So if this is our energy required to create that particular fracture, then if we assume piece to be a thickness of, here's a variable b into the page. Okay, so back up to my figure here. We're assuming that this is like a thickness of b into the page. Then the total area that was created by the fracture is delta A times B, obviously. All right, so it propagated some amount, delta A, and if that's consistent across the thickness or across the width of the particular piece, then the total area that you opened up when you did that fracture is delta A times the width into the page, which is B. So this will have something like meters squared. Yes, area in meters squared. Woo! Past 7th grade. Good job. All right. So finally, the critical strain energy release rate for this event is G, here I'll say 1C, since we're in mode 1, is this D on A, or for us, this will be 1/2 delta final P2 minus P1 on delta A times B, or more commonly you'll see this as G1C is equal to delta F P2 minus P1 all on 2 delta A times B. There you go. That's how we come upon that particular solution to determine what is the energy associated with that particular fracture. This is in joules per meter squared. All right. So that's where we're going to stop today. This is the energy associated with one singular fracture event. If you know the crack advance, delta A, you know the width of the sample into the page B, you know the maximum amount of displacement and the amount of force that was lost during the process. So more or less you know this load displacement curve, then there you go on your way determining what is the energy associated with fracture for this particular sample. And remember that this strictly was for pure epoxy material. We're going to talk about multiple fractures in the next lecture, and we'll get into composites as well. Okay, thanks for coming.